In this video, we're going to learn about stoichiometry. So you already have a basic understanding of stoichiometry. That is, you can determine how much stuff you can make in a reaction from some given amount of reactant. So from what you're starting with, if you're given a certain amount of how much you're starting with, you can determine using stoichiometry how much you can get. Okay, so we do simple stoichiometry at home all the time. So like for me, my recipe, which is the saddest ham sandwich in the world, is 2 slices of bread, 1 slice of ham, and that produces 1 ham sandwich. Okay, so if we need to make 2 ham sandwiches, we're going to need 4 slices of bread and 2 slices of ham. Okay, so if we have this reaction here, which is 2 hydrogen molecules and 1 oxygen molecule react to form 2 water molecules, we know that in order to make 2 moles of water, we need to start with 2 moles of hydrogen gas and 1 mole of oxygen gas. But if we want to make 4 moles, we basically have to double everything that what we have. So that's using what's called the mole ratio. Okay, and the mole ratio is the ratio of the coefficients in your balanced chemical equation. So I might just want to write that down. So, oh wait, it's already here. The ratio of the coefficients in a balanced chemical equation. So if you have a balanced chemical equation, you can find out, and you know something about one thing in that equation, you can determine the mass of something else, the number of moles of something else, the number of particles of something else. So really, as long as you know something about some member of a chemical reaction, you can figure other things out. So going from moles of substance A to moles of substance B, that's called your mole ratio. And that's determined again by your coefficients in your chemical reaction. All right, so let's say I have 5 moles of substance A and I want to know how many moles of substance B. Well, I'm just going to use my mole ratio to get me there. Now, let's say I'm given a certain mass of something. Okay, let's say I'm making this water recipe here. Okay, let's say I'm given that I want to make 15.5 grams of H2O. Well, I can go from grams of water, mass of water, to moles of water. We learned about that when we learned about moles. We can use our molar mass to get us there. Okay. Now our balanced chemical equation will take us from the moles of water to the moles of, let's say, hydrogen that we need to get there. Okay. And then to find out how many grams of hydrogen, so go to mass, I would just use my number of moles of hydrogen to determine, using my molar mass, how many grams. And we can do this for all of these different variables here. So let me just erase what I've got here. So if you want to go, I guess I didn't need to erase molar ratio, but whatever. If you want to go from moles of substance A to moles of substance B, you're going to have to use your mole ratio. Gots to. Okay. If you want to go from mass of something to moles of something, you're going to need to use its molar mass. Same thing here, molar mass. If I'm given a certain number of particles of something and I want to go to moles, I'm going to have to use Avogadro's number, 6.022 times 10 to the 23. Okay, same thing here, 6.022 times 10 to the 23. Okay, so let's do a few examples here. And I put this roadmap on each page so that we can kind of trace our path. Okay, so Ammonium sulfate is made by this reaction here. Let's see, equation. Oh, that's not a highlighter. By this reaction here. 2 ammonias, 1 sulfuric acid gives us 1 ammonium sulfate. So if I want to make 14.8 moles of ammonium sulfate, how many moles of sulfuric acid were required? So we're starting with moles of ammonium sulfate. That's what we're given. And we want to get to moles of sulfuric acid. And that's it. That's as far as we want to go. Okay. So let's take a look. We've got 14.8 moles of NH4 to SO4. Okay, now I know I need to get rid of moles of ammonium sulfate and I have to use my mole ratio. So in my chemical equation, my coefficient here is 1. So for every 1 mole of ammonium sulfate, I used 1 mole of sulfuric acid. See how the coefficient there was 1 mole of sulfuric acid. This is why it's really important to label everything. Okay, so now moles of ammonium sulfate cancels out, and our answer is given to us in moles of sulfuric acid. Obviously, you don't really need to put this in a calculator because it's a 1-to-1 ratio. So 14.8 moles of H2SO4 is your answer. Okay? All right, so let's go to the next one. If I have 1.654 times 10 to the 23 particles of ammonia, that's NH3, how many moles of sulfuric acid are required to react to it? So let's start with what we're given. Let's go where we begin. We begin here with the particles of substance A. Particles of substance A. Okay, and where we want to end up is right here, moles of substance B, moles of sulfuric acid. Okay, so we need to go from particles of ammonia, particles of NH3, to moles of NH3, to moles of H2SO4. Okay, so this adds another step. So let me just do my whole path. But that's okay, we're pretty good about doing our little T-chart, so fun. Okay, so if I have 1.654 times 10 to the 23 molecules of NH3. I know I put particles there, it doesn't really matter. Now I need to get rid of molecules and get moles, so I need to divide by 6.022 times 10 to the 23. So for every 1 mole of NH3, there are 6.022 times 10 to the 23 molecules of NH3. Okay, so now my unit molecules of NH3 is canceled out, and I'm left with moles of NH3. Okay, so now I'm here. Now to switch over from ammonia to sulfuric acid, okay, because it doesn't matter if they're on the same side of the equation or not, that does not make any difference. Okay, so it's a 2-to-1 ratio. There's 2 ammonias for every 1 sulfuric acid. So there are 2 NH3, 2 moles of NH3 for every 1 mole of H2SO4. Okay, so now we would cancel out moles of NH3 and we'd be left with moles of H2SO4. So we put this in our calculator. 1.654 times 10 to the 23rd divided by 6.022 times 10 to the 23rd divided, that whole thing, divided by 2. Okay. And for sig fig's sake, so for the number of digits, remember we're going to go back to our original number. Okay. So this one had 4 digits in the original number, so my answer will have 4 digits. So I got 0.1373 moles. Notice that for this one, we didn't need our periodic table, we didn't need molar masses, we didn't need any of that, okay? Because the masses are irrelevant there. Oh, look, particles to particles. That's what we got going on here. We have particles of ammonium sulfate, so ooh, I got to get used to doing this, switching. NH4 2SO4. And we want to go to particles of substance B, which is sulfuric acid, H2SO4. Okay, so to make our path there, we have to go from particles to moles, moles of one to moles of the other, and then from moles of that thing to particles of that thing. Okie dokes, let's do it. Okay, let's go crazy. All right, so we were given that we have 2.27 times 10 to the 24 particles of ammonium sulfate, NH4, to SO4. Okay, so now we want to get rid of particles and get moles. So for every 1 mole of ammonium sulfate, we had 6.022 times 10 to the 23 particles of ammonium sulfate. Okay, so now we have gotten rid, use this, of particles of ammonium sulfate. Cool beans. Okay, now let's get rid of moles of ammonium sulfate, because now we're here, and go to moles of sulfuric acid. Ooh, look at that. That's a 1-to-1 ratio. So for every 1 mole of ammonium sulfate, we got 1 mole of H2SO4. So now we're in moles of H2SO4. And for every 1 mole of H2SO4, you get 6.022 times 10 to the 23 particles. Oh, I got too close to the edge there. Sorry. Of H2SO4. Okay. So moles of ammonium sulfate cancels, moles of sulfuric acid cancels. And I hope you're seeing something a little silly about this problem here. Okay. We are dividing by 6.022 times 10 to the 23 here, multiplying by 1 over 1, and then multiplying by 6.022 times 10 to the 23rd. So because it's a 1-to-1 mole ratio, it's also going to be a 1-to-1 particle ratio. Because remember, the amount of particles in a mole doesn't change from one molecule to the next. So our answer here, annoyingly, and yes, you would have to show all your work, is going to be 2, you don't have to put this in your calculator because everything cancels out, 2.27 times 10 to the 24 particles of H2SO4. Okay, if we want to make 150.00, so 150.00 17.00 grams of NH4 to SO4. How many grams of ammonia will we need? Okay, so we have to get to grams, questionable amount of grams of ammonia. Okay, so this is going to require probably a lot more time just because it involves masses, and so you have to calculate your molar masses. But let's do our pathway either way. So we have a mass of ammonium sulfate, and we're going to use our molar mass to get to moles. Then we're going to use our mole ratio to get to moles of ammonia. Then we're going to go use our molar mass to get to grams of ammonia. Now, just like a cooking show, I'm going to give you the prepared molar masses, okay? Because I know that you all know how to calculate a molar mass, and I don't want to take up a ton of time in this video, okay? So the molar mass of NH4 to SO4 is, let's see, I'm on the wrong page. Here we go. We've got 132.13 grams. Okay, and the molar mass of H2SO4 is 98.07 grams. Okay, so let's do this, okay? So we're going to start again where we're given, what we're given. We start with 150.00 grams of ammonium sulfate. And now we need to go from grams to moles. And we already know how to do this. Okay, we have to get rid of grams, put grams in the bottom. Ammonium sulfate. And get 1 mole of ammonium sulfate. Okay, so now grams of ammonium sulfate cancels. But I have to fill that number in. And that number is 132.13 grams. So now I've made it to here, the number of moles of ammonium sulfate. Okay, next, we're going to get rid of moles of ammonium sulfate and get moles of ammonia. So we have to go back to our chemical equation. Beep, 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 here it is. For every 1 mole of ammonium sulfate, it uses 2 moles of ammonia. So for every 1 mole of NH4 to SO4, it requires 2 moles of ammonia. And hey, guess what Mrs. Berger just realized? I gave you the molar mass of sulfuric acid and not the molar mass of ammonia. My bad. The molar mass of ammonia up here is 17.031 grams. Okay, so now I'm here. Getting rid of moles of sulfuric acid, not sulfuric acid, ammonium sulfate. Now we have moles of NH3. Okay, cool. So now, for every 1 mole of NH3, it requires 17.031 grams of NH3. Okay, so moles of NH3 cancels out. So we're going to put this in our calculator. 150.00 divided by 132.13. Okay, enter, times 2. Okay, times 17.031. Okay, reminding ourselves that this mole ratio does not count towards sig figs, towards the number of digits. Okay, so our answer is going to have these 5 digits. Okay, and the answer to that is 38.669 grams of ammonia. So we went from grams of one substance to grams of another substance. Okay, using the stoichiometry roadmap. Okay, we got one more problem that goes along with this equation. We have grams of sulfuric acid, and we're looking for molecules of ammonium sulfate. Molecules. All right, I said it right now. Okay, so let's see. We're starting with a mass of something, 18.5 grams of H2SO4. And we want to get to particles, molecules of ammonium sulfate, NH4, 2SO4. How many particles? All right, so let's do our path. All right, from mass to moles, we're going to need our molar mass. From moles to moles, we're going to need our mole ratio. And from moles to particles, we'll need Avogadro's number. Okay, so I think I have space over here to do it. Let's try. And I had written before accidentally, but 1 mole of H2SO4 weighs 98.07 grams. Okie dokes, so let's do it. Let's get this bread. 18.5 grams of H2SO4. Okay, we have to get rid of grams and get moles. So use our molar mass here. There are 98.07 grams of H2SO4 in every 1 mole of H2SO4. Okay, and our mole ratio is a 1-to-1 ratio. Okay, because it's a 1-to-1 here. So we're going to say now we have made it to here. So I'm going to cancel off grams. So now to go from moles of sulfuric acid to moles of ammonium sulfate, we'd say for every 1 mole of H2SO4, you also get 1 mole of NH4, 2SO4. Okay, so to take this home, we've already gotten to here. We would just need to, so moles of H2SO4 cancels out. For every 1 mole of NH4, 2SO4, you get 6.022 times 10 to the 23 molecules NH4, 2SO4. Okay, so let's put this in our calculator. Okay, so 18.5 grams divided by 98.07. Okay, this 1-to-1 step, you can do it. If you want to multiply by 1 and divide by 1, be my guest. You should probably get a hobby if that's something you're interested in doing. And then multiply that by 6.022 times 10 to the 23, putting it into the calculator correctly, not using carats, using 6.022 second comma. Okay, if you have a regular calculator or on the iPhone, EE, but not, and then doing 23. You don't do times 10 to the, okay? All right, so we have this problem, and let me get my answer here. So we started with 3 digits, so our answer will have 3 digits. The exponent doesn't count towards our number of digits. So our answer is going to be 1.15 times 10 to the 23 molecules NH4, 2SO4. Okay. Hopefully this is starting to make some sense. So basically you can go anywhere and you can stop at any point. So that not every problem has 4 panels like this problem here does, okay? Especially if it's just like a mole to mole. All right, so our next example involves a combustion reaction, which is a carbon compound reacting with oxygen. So we're given molecules of CH4. So we're given 9.32 times 10 to the 23 molecules of CH4. And we want to get 2 grams of carbon dioxide. Okay, so I know that I'm going to have to go from particles to moles using Avogadro's number, from moles to moles using my mole ratio, and from moles to grams using my molar mass. Okay, so the only things molar mass that I'm going to need in this problem is carbon dioxide. So the molar mass, the MM of CO2, equals 44.009 grams. Okay, so let's start this problem. We've got, you know what? I'm going to start it down here. I'm going to be a rebel with a cause. It's already written down for me there. All right. So I have to get rid of molecules and get moles. Cool. In 1 mole of CH4, there are 6.022 times 10 to the 23 molecules of CH4. That number, 6.022 times 10 to the 23, is probably going to be burned into your brain for the rest of your life. Just so you know. All right. So now we're getting rid of molecules. And now we have to switch over from moles of CH4 to moles of carbon dioxide. And it's a 1-to-1 mole ratio. How fun is that? For every 1 mole of CH4, we also get 1 mole of carbon dioxide. Okay, so now we're here. And now we just need to go from moles of carbon dioxide to grams of carbon dioxide. Okay, so for every 1 mole of CO2, you get 44.009 grams of CO2. Okay, let's cross off things that are gone. Boom. Okay, so sig fig wise, we can have 3 digits here. So we're going to type in our calculators 9.32 times 10 to the 23rd divided by 6.022 times 10 to the 23rd. Again, this 1-to-1, if you're bored, go ahead and do it. And then times 44.009, okay? And I actually did not write the answer down in my little answer key here, so I actually have to put this in my calculator right now. How annoying of me. 9.32 23 divided by okay, I got 68.1 grams of CO2. Cool beans. Cool lima beans. All right. Last one. Okay. I hope you guys are doing okay with this and not really having to look at that roadmap. Okay. It's not going to be given to you on tests and quizzes and things like that. All right. So if we're starting with 41.9 grams of O2, and we want to go to moles of carbon dioxide. We only want to go to right here. Moles of CO2. Okay. Well, we need the molar mass of O2, and I think a lot of you know that one. It's 31.998. sorry, honey. Sorry, dears. 31.998 equals the molar mass of O2. Okie dokes. So we have 41.09 grams of O2. We have to get rid of grams and get moles. So for every 1 mole of O2, there are 31.998 grams of O2. Okay, now we're going to switch over to moles of carbon dioxide. Okay, for every 2 moles of O2, we get 1 mole of carbon dioxide, and that's as far as I have to go. Okay, I get to stop right here. Okay, let's put this in our calculators. Oh, I realized I put 41.09. That's not true. It's 41.9. Okay, so the answer here, so what we'd be doing is 41.9 divided by 31.998 and then divided by 2. And our answer will be 0.655 moles of O2. Nope, carbon dioxide, CO2. I didn't write things down. There we go. Okay, so that is going to be your notes today for stoichiometry. You're going to have some practice problems to work on your own. Have a great day.